In this video, we're going to be talking about centripetal force. Specifically, we want to define what is the centripetal force and how we can incorporate that into what we already know about forces with Newton's second law. We want to solve circular motion dynamics problems because there are a lot of them and they're pretty interesting. So what do we mean when we say centripetal force? Well, when I say centripetal force, I mean the force that causes motion. But it is not a new kind of physical force. It's not Fg or Fn or Ft or anything like that. It is really just the net force or the sum of the forces in the radial direction. It's just like some of the forces in the x or some of the forces in the y. And in that way, it never shows up on a free body diagram. This is the sum of the physical forces. In fact, you already know how to draw free body diagrams for any forces. This is no different. The only thing we have to watch out for is the axes. Instead of talking about x and y, we're going to talk about radial, tangential, and perpendicular to the circle. So, for example, when we're talking about linear motion, right, we've got x and y coordinate system, we sum the x's, we sum the y's. In circular motion, we have radial and tangential, and you can't see it in this picture because it would be coming out of the page at us or the screen at us. That would be perpendicular. And the one we really care about most of the time is the radial component, because the sum of the forces in the radial is what we call centripetal force, and that is what is equal to the mass times the centripetal acceleration. Really just restating Newton's laws in a different dimension. So the big key to all of this is setting up your coordinate system, just like it always is, but now it's a new scenario. So for linear motion, we use x, y, and z. For circular motion, we use r for radial, t for tangential, and p, or the perpendicular symbol, for perpendicular. So we have a robust problem-solving strategy, and you'll notice that when we solve circular motion problems, it's basically the same. We're starting with the free body diagram. But now, instead of just setting up a coordinate system x and y, we first need to identify where the center of the circle is, which may not always be obvious, so it's good to think about. Then we're going to sketch out our axes, radial and tangential or perpendicular, and this should be sort of overlaid on where the object actually is, not based on the center of the circle, because the object will never be there. Then we add up the forces or find the components that act radially. Into the circle is positive generally, and out of the circle is negative. And then we write out something like this. The net force on the radial equals the centripetal force, which is m acentripetal, which equals m times v squared over r, because the definition of centripetal acceleration is v squared over r. And every time you solve a circular motion problem, you should write out that whole thing. That is stating all the things we know kind of law-wise about how uniform circular motion behaves. It's got Newton's laws in there. It also has some kinematics. The definition of centripetal acceleration, v squared over r. So let's take a moment to think about a vertical yo-yo. You're spinning a yo-yo up and down. So at the top is the top of the circle, C is at the bottom, and the other positions are there. We want to draw some free body diagrams. We want to think about what the net force radially is. So we need to call into the circle positive and out of the circle negative. And oops, I somehow moved A out of the way. But we're going to get the equations for a centripetal force for all of those points, all 5 of them. So we start by drawing the radially inward direction. Notice this is overlaid on top of the position of the object, pointing toward the center. And then the tangent direction. I haven't made it go clockwise or counterclockwise. It really doesn't matter here. We don't know which way it's spinning around, but we know that that's the tangential direction. So now we can start adding up forces. So we'll start with the first one. A, the force of gravity is pulling down, and if there's a string attached, the tension could also be pulling down on it. And so if I were to write out my Newton's second law equation for this circle, I'd say it's tension force plus gravitational force equals mv squared over r, because that is what Newton's second law tells us. For B, the tension is into the circle and gravitational force is tangent to the circle. So only the tension shows up in my Newton's second law equation for the uniform circular motion. For C, we have tension into the circle and the force of gravity out of the circle, which means our net force is tension minus the force of gravity. In is positive, out is negative, because in is the way we need it to, the net force to be, to cause it to go in a circle. In D, we have components of the force of gravity. Tension is still radially inward, but we have a little bit of gravitational force that's out of the circle that we have to subtract. And there's also some that's tangent to the circle that is not going to show up in this equation. And similarly, for E, gravitational force is pulling partly into the circle. So this time we add the radial component. So let's look at some examples and see how this plays out. If you have a turntable, right, record player or something like that, and you place a mass on it, what force causes the object to move in a circle? Well, we got to draw our free body diagram first. And so I'm going to always draw it sort of looking at the object sort of tangent into the page. And so that means there's a gravitational force down and a normal force up that are perpendicular to the path of motion. And then there's going to be a static frictional force pulling it in, keeping it from sliding off the turntable. As it accelerated, there was probably also a force tangent to the circle, but we're not interested in that for this particular discussion, right? If we can add our coordinate system, what you might call the positive x or the radial direction is those two lines. The centripetal force then is equal to the force of static friction. That's the only force acting radially. Here's another example. Janie swings Jimmy with a 1 meter long rope in a horizontal circle. What is the tension in the rope? I mean, this might be a slightly silly circumstance, but the radial sum of forces should be equal to the centripetal force. And that is just the force of tension. So that's equal to mv squared over r. 45 kilograms is the mass of the object going in the circle, Jimmy. And the radius of the circle is 1 meter. So we end up with 405 newtons. So we can go back to the turntable. I've got a bag of sand. If you look carefully, it looks like it's a bag of flour, but whatever. And it's going around in a circle. We have our free body diagram: normal force, force of gravity, force of static friction. The net force in the radial is that static frictional force, right? The loop-to-loop of a roller coaster, if you're going up and around and around and around. At the top, the normal force from the track pushing down on the cart or the object are going to be pushing together with the force of gravity to get the centripetal force. If you're in one of these barrel rides, Turkish Twist is the name of one of them, the radial sum of forces is just the normal force pushing on your back, holding you in, right? The force of gravity is down, the normal force is in, and it's static friction that keeps you from sliding down the wall, right? We can go ahead and actually do the problem here. We could say, well, we're given enough information about your mass, 1 second to go around once. I think that's what it says. Yeah, 1.5 seconds, excuse me. So that's the period. We know the radius of the circle, so we can calculate the speed. Then we can use that to calculate the normal force, which is about 3,500 newtons. If you're going around a curve, if you're driving around a circle, right? Coefficient of friction between the road and the tires is 0.8. This is static friction. We draw the free body diagram of the car. You've got static friction into the circle and normal force and force of gravity. It's that static frictional force that's keeping it from skidding out of the circle. We can say the net force in the radial is the static friction, equals mv squared over r. And you might ask a question like this: at this speed, how small of a circle could we get? Notice the smaller r gets, the bigger the force will be, and we can get to Fs max. So if we solve that, mu times the normal force, which in this case is mg, gives us the maximum static frictional force, and that's equal to mv squared over r. V is given, mu is a given, g is a given, so we're just solving for the radius, and that ends up being about 51 meters. Right, that mass cancels out, which is nice. So the mass of the car doesn't really matter here, right? And that's good, because if it did, then you getting into or out of your car as a passenger while someone else is driving it would change the frictional relationship and might make it so it was unstable to drive. Should not be so good. All right, so that's that. The basics of dynamics, or using Newton's laws for problem solving in circles.